Hello everyone, you're welcome back to class. In this part 4, we are going to be looking at the generalized material balance calculations. So let's get right into it. For as many that this is your first time of watching this video, I would like you to go back to the videos of the part 1 to part 3 of the general materials balance. In part 1 to part 3, we treated the reservoir types and drives, the Schilthius material balance assumptions, the material balance derivations, Havlena and Odeh heavy expression, and then more. You learned so much more. In this part 4, we're going to be looking at a recap of part 1 to part 3 quickly, examples, and then I give you some exercises. Okay, so a quick recap of part 1 to part 3. Um, in the videos of part 1 to part 3 MBE, we looked at the Schilthius material balance equation. For those that watch it, I'm sure you can recollect this equation 25, this equation 26. Here, there is no pressure maintenance included. Here we have the pressure maintenance, water injection and gas injection, pressure maintenance, and here we have the Havlena and Odeh material balance equation derivations. You have the linear equation of the Havlena and Odeh giving you this for without pressure maintenance, and here with pressure maintenance, including also the water and gas injection. So the Havlena and Odeh express the MBE, the Schilthius MBE in a straight line. Okay, so we look at different cases as well. The case 1 for the volumetric undersaturated oil reservoirs, given this, we derive this F equals N to EO plus EFW, this showing the expansion of oil, and this showing the expansion of oil and gas, and this showing the expansion of water and the rock, okay, within the reservoir system. So this is for volumetric undersaturated oil reservoirs. And this is the expression, Havlena know the expression for the volumetric undersaturated saturated oil reservoir. So when you have the saturated oil reservoir, here your RP is not equals to RS, okay? RP is not equals to RS, not equals to RSI. And then you have you either have your EFW, and it could as well be neglected depending on the question. And then you have the volumetric gas cap drive reservoir. We derive these equations as well. And then we look at different situations by which you can have obtain your hen, that's OIP, obtain your gas cap size, hem or slope. When you have N, when you're giving hen, here you're giving hem, you obtain N. Here you're giving N, hen as well. You obtain hem, and in the third case, M and hen are not both given. Okay, so this is the case 3. And you have the case 4 for the water drive reservoir. Here you have the WE is not equal to 0. You have the plot as well. Okay, and then in case 5, there's a video which you be expectant. I'm going to be treating gas reservoirs. Okay. So this is an in-class discussion. I want to pause this video for a while. Look at this slide. It can be hard to identify familiar terms, drives, and discuss them. So you should be able to identify your gas injection, water injection, your gas cap drive, solution gas drive, your condensed water expression, your water drive, your raw compaction drive expression. So each of these expressions, to be able to identify them, is the same thing as your equation 25 and 26. Yeah, in some text, you could find a bit of differences, but looking closely at them, they're actually the same. CF, don't forget, is the raw compressibility, and Pi minus P is your dP. GP minus GI, your gas, GI is your gas injection, water injection, your W high, you have your water produced, you have your water formation volume factor. So it's basically the same for all techs, and then you have all this for your secondary drives or your pressure maintenance, water injection and gas injection. And here your primary drive, okay, your gas cap drive, we treated all in the part 1 to part 3 of the video, so you can avail yourself of the videos on the channel. Go back, go watch them. The primary drive indices, you have your solution gas drive, your water, collate water expansion, and rock compaction drive. So if you're also asked to identify familiar terms or terms within the equation, you should be able to infer your BG, your BO, your RSI, your RP, your WP, your WI, your BT, especially two-phase formation volume factor. Difference between your BT and your BT high, difference between your RS and your BO, your RS, your RSI, your BW, your change in pressure, or your G and your BWWP. So you should be able to identify the terms and then as well discuss them. So you can be asked to discuss the drives, the terms, and yeah, I'm sure you'll be able to handle that. So you can take some time, uh, take each one of them and see if you can recollect what we have learned so far. All right, so you're welcome back. We'll be treating the example 1. Just a minute, let me put this down a little, okay? So example 1, we have the question here saying, using the following data, determine the whole high P by the Havlena and Odeh equation, assuming there is no water influx, okay? So W is 0 and no initial gas cap. So you remember your initial gas cap, your gas cap is M. So M is 0. One interesting thing about this question, because you must first of all understand the question, understand the reservoir that is being described in the question, the state of the reservoir, the drives in play during the production life of that reservoir. So here we're giving the bubble point pressure 1,800 psi. So the pressure starts from the bubble point pressure and then reduces to 142, 1367, 1053, or psi below bubble point pressure. Okay. So you have your NP produced, your RP, solution, your gas oil ratio produced, your BT two-phase formation volume factor, your RS, and then your BG. And then you note that here there is no oil production. Below here, it was discovered that the evolving of gas from your oil. Okay, so here there's no oil production. Solution gas, all the solution gas was equally, and other gases that may be existing within the pores of your reservoir are also locked up within the reservoir. So there is no production, solution gas production, 0, okay, at the bubble point pressure. At BT, note that the first value here is your BT high. The first value here is your RSI, and every other value is your RS. Here, every other value is your BT. For your BG as well, the first value is your BG high, and every other value your BG at the corresponding pressures given, corresponding pressures, okay? So we are asked to determine the whole high P, that's your N. Oil originally in place, okay, your head. So we go right into it. So you remember for saturated oil reservoir, the Schilthius equation and the Havlena and Odeh derivation. So we have your F equals this, and then you have all this equals 0. So you go back to the part 1 to part 3 video so that you can understand why we made all this to be equal to 0. Basically because these are saturated oil reservoir. And how do we know it's saturated? Because you have your bubble point pressure, and below it you have production of production of gas, solution gas produced, solution gas within the reservoir equally reduced. Okay, so you have your equation one, your F equals this, and then your F to the right hand side equals this, and your F to the left hand side equals this. So here, RP is not equals to RS, and it's not equals to RSI. So you have a changing RP, you have your RSI, and a changing RS with pressure. Okay. And then we note that we have BT, okay, because if you remember your RS versus pressure profile, you have your BT at a certain point below the bubble point pressure because your reservoir now exists in a two-phase, the oil and the gas. So you have your BT, you slot in your BT, okay? So you have your BT and then you have your F. Your F equals this, BT minus BT high. Okay, so we are just applying all the equations that we have learned in part 1 to part 3. So you can avail yourself, like I said, of the video so that you understand how we came by all the equations. Okay, so we are trying to estimate N, the OIP, original oil in place, and then making any subject of formula, we have this. So we calculate this, slotting in on the values. We have the NP, we have the BT, we have RP minus, we have RP, we have the RSI, you remember. We have the BG, we have BT, and we have BT high, okay? So for at each pressure, so for at this pressure, we slot in all the values, and then we have for 6.54 mm STB. Each M is 3 zeros. This is times 10 to the power 6 STB. At here, 1367 PSI, we have 44.17 mm STB, and then N at 1053 PSI, the lowest pressure given below bubble point pressure, we have 49.7479 STB. So I wanted to confirm these values, punch your calculators, your adding machines, and see if these values are correct. If you're going to be taking your physical exams and you have a question such as this, you need to punch your calculators or make use of your Excel, feed in these equations, and then see if these values are actually correct. Okay, so we take an average of the N, average of this. So you also confirm we have 48.9 STB. So what we have done basically is to estimate N at each pressure. Estimate N at each pressure. What's the OIP at this pressure, the OIP at this pressure, and the OIP at the last pressure. And you observe we did not calculate N for the first N, that's at 1,800. And go back so that you can see. Okay, we didn't estimate pressure at here at 1,800 because basically NP was 0, RP was 0. Okay, so if you slot in NP at 0, NP at 0 turns the whole equation to 0. Okay, so RP at 0 as well, NP at 0, so turns the whole equation at 0. And then here we have RSI, RP minus RSI, RSI here RSI, you have your RSI, okay? But here you have your BT minus BTI, that will be BTI minus BTI, because at the initial pressure, 1,800, they are both the same, so renders this to be 0 as well. So I believe you understand that, how to estimate your N at each of the pressures. You can also try and find out why you have 46 at just below your ball point pressure, okay, and then you have a bit of reduction, and then it goes higher here again, okay. What could have been responsible? Did any other drive come into play? What do you think would have been responsible? This is 48.9 times 10⁻⁶ XTB. Like I said, try to confirm this value. Okay, so calculate the recovery factor at the varying reservoir pressure. So you remember your recovery factor. I want you to calculate it at each of these pressures. Each of these pressure, calculate your recovery factor. Your fractional recovery MP over N. Okay. All right, so such an interesting example we have here. Example 2, a volumetric undersaturated oil reservoir has a bubble point pressure 4,500 psi. I have a psi here. Okay. The initial reservoir pressure is 7150 psi, and the volumetric calculations indicate the reservoir contains 650 STB of oil initially in place. The field is a tight, naturally fractured chalk reservoir and was developed without pressure support by water injection. So there was no pressure support, there's no water injection. And then the following additional data volumetric calculation was given. Okay, so you have your SW high 43%, that's your water saturation. You remember your SO plus SG plus SW equals 1. Okay, so you have your water saturation to be 0.43. Your rock compressibility in the order of 10 raised to the power minus 6, 3.3, and 10 raised to the power minus 6. You understand what this means? Okay, I believe we treated that as well. Your BW, 1.0 barrel per STB, your CW also in the same order with your CF, and then your PB, 4,500 PSI. Okay, so going back to the question, it's an undersaturated oil reservoir. You have to understand that. The initial pressure was 7150 PSI. Okay, and then volumetric calculations, initial calculations that were done not using MBE shows that it contains 650 STB of initial oil in place. So we want to confirm from the material balance equations using it to be sure compared to the volumetric calculations. Okay, if the volumetric calculation underestimated or overestimated the whole IP within the reservoir system. Okay, so let's get right into it. So we can have questions here. I have some for you, or we'll be calculating a hen, estimating the hen, and I would like you to lay your hands on B to F. We have actually treated all these in the videos, part 1 to part 3. So it's just serve as a revision for you. Okay, so the first question says, calculate the initial oil in place by using the MBE. And compare with the given volumetric estimate of N, explain the difference, if any. So if there's any difference between the volumetric estimate and then the MBE estimate, you have to explain why there is a difference, if any. Okay, suggest drives under which this reservoir can be produced both in the saturated and undersaturated states, and give reasons for your answer. So look at the pressure profile above point pressure, which is the undersaturated state, and below the bulb point pressure, which is the saturated state, and suggest if there are drives, okay, based on what we have treated in part 1 to part 3. Okay, what changes are likely to occur within your reservoir system as pressure declines from P high to PB? So what changes are likely to occur as pressure declines from your initial reservoir pressure, okay, to your bulb point pressure? I believe we've taken a class to this effect, so we should be able to state the different changes likely to occur. Do you have a slight expansion of oil? Do you have solution gas within the system? Do you have expansion of the solution gas? Okay, these are some of the answers that are expected of you, and for you to explain how it happens. You can also support your answers with a profile, possibly your pressure, your RS pressure profile, your BO pressure profile. Okay, why is oil produced, the oil produced, that's your NP below PB, why is it higher than that of the undersaturated state? So the oil produced below your PB, why is it higher than oil produced in the undersaturated state? Okay, so you also want to check text and videos and see if you can give this question a shot. Okay, plot a fully labeled RS versus pressure profile, and then a BO versus pressure profile. BO versus pressure profile. Okay, so let's look at the production profile we're giving data for the question. Wow, the initial pressure was 7150. I believe you still remember that. Let me go back to the question. Okay, 7150 psi. Okay, so let's go back. So we have pressure ranging between 7150 to 2800 psi. And an interesting one we have here, we're giving the production rate, oil production and gas production. You have the oil production here and SCB per day. You have the gas production in SCF per day. And then you're familiar with this, your BO, your RS. Don't forget this is your BOI, 1.743. Your RS, this is your RSI 1450, and then your BG, gas formation volume factor, which actually started at your bubble point pressure. Okay, just below your bubble point pressure. Okay, then we are given bubble point pressure. Let's check it once again. Okay, bubble point pressure to be 4,500. Okay, blood pressure to be 4,500. So BG, gas formation volume factor, so shows that just below your bubble point, you have gas evolving from your reservoir, okay? And that's why you have your BG from here. This is the formation factor, your BG high, and every other ones are your BG at the corresponding pressures, okay? And then your NP, at the initial reservoir pressure, there was no production. Upon slight reduction, okay, you can see from 7150 to 4950, what do you have? You have initially there was no production, and then you have gradual production as a slight reduction in pressure occurs. You have from 8 to 23 to 36 to 43 mmSCB. Okay, and lastly, you're giving your RP, that's the solution gas produced to the surface, solution gas produced to the surface. RS, you know the difference between your RS and your RP. Your RS is the solution gas within your oil system in your reservoir. Okay, the solution gas within your oil in the reservoir. Okay, dissolved in your oil in the reservoir. While this is the solution gas produced to the surface. So solution gas produced to the surface, and the solution gas produced to the surface is not only from it's not only from RS, it's not only from RS. Basically from here, from 43560, we have production of RS along with RP. Okay, because here we have the gas formation volume factor. We see that solution gas was actually constant. 1450 was constant, and at below the bubble point pressure, it's reduced. So you have 1450 minus 1323. Okay, so we have other gases from the micropores, okay, that could also constitute parts of the GOR produced to the surface. And this is GOR is the volume of your gas to the volume of your oil produced to the surface. Okay, so you have your RP, there. Okay, so we are estimating N. We have to calculate N for the undersaturated state. N for the undersaturated state. So remember, okay, so before I go on, let me mention that you're going to be calculating N for this question, but we are going to be treating the question in two phases. We'll treat the undersaturated state of that reservoir and the saturated state of the reservoir. We know that the reservoir pressure actually reduced up to a certain point and crossed to the saturated state. So the equations, the Schilthius equations handling the undersaturated state is different from the Schilthius equation, the Havlena and Odeh solution handling the saturated state. Okay, so you have to understand that. If you don't fully understand it, please go back to part 1 to part 3. You will understand it. The videos are there. Okay, so for the undersaturated reservoir, you have your hem equals 0. Your hem equals 0. That's your gas cap. Your harp equals Harris equals Harris. WE and WP equals 0. And then the general material balance for the undersaturated reservoir, you have your HEF, you have all these. I'm sure you understand why we have all this by now. And then we estimate our EFW, okay, because we are estimating for each of the pressures under the undersaturated state of the reservoir. So we have initial pressure minus each of the pressures from the P high to PB, okay? And then we estimated for, in just a minute, let me push this up, okay? So we have for EFW, you have your BO high, the CW and SW given, okay, here. And then the estimated EFW gives this, okay? And then your HEO is BO minus BO high, okay? Remember I said we have corresponding BOs for each of the pressures, okay? So it's BO minus 1.743. So this equation 3 and equation 4, okay? I'm sure you can arrive at all these. You have your CW you've been given, you have your SW you've been given, you have your CF, all these are constants you've been given. Here, your SW equals SW high, so you've been given 0.43, okay? So you estimate this, you estimate your HEO as well, okay? So we are going to be slotting these equations to obtain our N, to obtain the N. We'll also obtain the F. You know what F stands for under saturated state. Okay, so let's go. So we slot in, making use of your Excel, your calculation, your machines, you will obtain these values. You have your F, you have your HEO, okay? Remember, 7150 to 4,500. That is the undersaturated state, which is the first aspect of estimating our N, okay? The whole high P. So you have your DP, which is the 7150 initial reservoir pressure minus the subsequent pressures. So you have 550, 1350, 2200, and 2650. Then you have the estimate of your EFW from the equation 3, okay? And then you have your N equals F divided by EO plus EFW, okay? I hope you understand this. Let me go back a slide. Remember your F, NPBO, okay? Then we estimated the EFW. We estimated the EO at each reservoir pressure, okay? So, and that's what we have here. That's what we have here. So the N obtained at each reservoir pressure in the undersaturated state is what we have here. 574 mmSTB, 562, 564, 557, okay, mmSTB. Okay, so let's go on. The estimate of N at the undersaturated state is the average of the obtained N, like we did in the question 1 that we treated, the example 1. Okay, so you had all that together, all this together, and take an average. Okay, so if you take an average, you are likely to have something close to this. So go into your Excel, can pause the video, go into your Excel, take all the values, type in the values, and calculate your HEO, calculate your EFW, calculate your F, and then estimate your N. Okay, so you have something close to this, 558. May not be the exact answer, but should be close to this, okay, which is lower by about 14% of the stated volumetric estimate, 650. So this is a bit lower by 14%, okay? So the uh, initial estimate, volumetric estimate gave 650 mmStB. The material balance estimate gave 558 mmStB. Okay, so let us go to the second part where we obtain our N for the saturated state of that reservoir. Okay, saturated state, all pressures below PB, all pressures below PB. So you have to understand that the behavior of your reservoir in the undersaturated state is quite different from its behavior in the saturated state. And as well, the Schilthius equation and the Havlena and Odeh derivation, which describe this behavior, are also quite different. So in the undersaturated state, you see that your RP equals RS equals RSI, which makes them all zero, okay? But here, in the saturated state, RP is not equal to RSI, is not equal to RS. Let me go back so that you can understand this, okay? So in the undersaturated states, RP equals RS. I believe you can see it from here. 1450 SCF per STB, and then 1450 SCF per STB, RP equals RS, okay? So you have here, you have here, okay? So just a slight difference here, almost equal, okay? But in the undersaturated state, RP is not equal to RS and is not equal to RSI, okay? So this is the undersaturated state. From here, saturated state, I beg your pardon, 4350, 4060. If you trace your RS, here you have 1323, your RP is 1576, and your RSI is 1450. So they are all different because in the saturated state, you have gas evolving from your oil. Okay, you have GOR produced to the surface. You have the RS continuously decreasing because there is evolving of the solution gas from within your system, your oil system, okay? Evolving gas dropping out of your oil system and then flowing to the surface. And don't forget your critical gas saturation. When the saturation of the gas that is evolved from your oil exceed the critical gas saturation, then it begins to flow to the surface, and you have gas at the surface, okay, produced to the surface. You have gas produced to the surface. Okay, so let's go on. For the saturated state, you have your F equals NEO and your NEO. Uh, this is your right-hand side, and this is your left-hand side, your F, left-hand side of your F. Your EO stands for this because RSI is not equal to RS, okay? And your N, from here, your N, estimate of your N will be F divided by your HEO, okay? So we take the pressures at 4350, the F estimated at 4350. You have equation, let me go back a little. This equation, NP into BO plus RP minus RSBG. Okay, so this was solved. This is a NP, NP. This is the, okay, multiplied by the BG. Okay, so you have 97.2156 mmStB. So you are asked to punch your adding machines, your calculators, or use your Excel and calculate the Fs at 4060 to 2800 psi. Then the EO as well. EO as well. The EO, you have BO minus BOI plus RSI minus RS BG. Okay, so you have it all calculated here at 4350. You have this. So you just slot in the values at this pressure. You have all the values in the on the table. Okay, so you have your HEO to be 0.1332. calculate the subsequent EOs at between 4060 to 2800 psi. Okay. And then you obtain your EFW. Because your EFW, you have changing pressure. Okay, I believe you remember. Uh, you have changing pressures from here. EFW, okay, your DP, remember, you have your DP, you have your DP, okay, you have your DP. Yeah, in this case, your EFW, that's the rock and water compressibility, is actually negligible. It's actually negligible. But here, it was added to this equation, to the solution of the Hen. It was, however, added in the saturated region. Ideally, it's usually negligible and then removed from the equation, but we want to see the effect. That's why we added it to it. So why it is negligible is because sometimes if you add it to it, you won't see the effect. Okay, whether you add it EFW or not in the saturated state, you may not feel the effect on the N, on the estimated N. But in this case, we decided to add it to it. Okay, so you have your N equals F divided by EHO plus EFW. Okay, so you have the estimated average N, the average N to be given as 570 mmSTB. So estimate your EFW, estimate your EFW at each of corresponding pressures. So the N is F divided by EO plus EFW, and the average N for the saturated state is 570 mmSTB. Okay, so let's look at them here. Okay, so you have the table here. You have the table. You see the saturated state. Okay, a bit of a gap here to show the difference between the saturated state, the undersaturated state, I beg your pardon, and the saturated state. Okay, so saturated state holds from your 4500 is your PB, actually goes with your undersaturated state because the evolving of your oil actually starts from just below your PB. So you have 4350 up to 2800. So when you're handling your saturated state, start from the pressures just below your PB. Okay. Um, so you have the F estimated, okay, the HEHO, for the saturated state, you have them here. Your change in pressures, that's 7150 minus each of the reservoir pressure, 7150 minus 4350, 7150 minus 4060 give this, 7150 minus 3840 give this. So you have all the pressures here. And then you have your EFW, okay, estimated for the saturated state. And then you have your N equals F divided by EO plus EFW. Okay, so you have your N, or your N estimated here. Your N, that's your OOIP at each of the pressures. Okay, so upon adding here, the average you have 570 mmSTB, 570 mmSTB. You can actually add for the saturated state as well and check the average. We check the average for the undersaturated state. You can check the average for the saturated state, and you can check the total average. So know the difference, the percentage difference between the volumetric estimate and the MBE estimate, the volumetric estimate and the MBE estimate. Does the volumetric estimate, does it overestimate OIP? Does the MBE overestimate OIP? Here we have 570 mmSTB. The estimate given from the volumetric calculation is 650. I believe you can still recollect that. Let me go back from the question. Okay. From the question, go back a bit. Okay, so you have, it says the initial reservoir pressure is 7150 psi and the volumetric calculations indicate the reservoir contains 650 SCB of oil initially in place. So why do we have a discrepancy? Why do we have from MBE, we have from the undersaturated state, we have the average of 558 SCB. From the saturated state, we have about 570 SCB. Okay, so let's look at the third question that says, what are the changes that are likely to occur? You have connate water expansion is a change that is likely to occur, okay, within your reservoir system. You have reduction in the entire pore volume, okay, reduction in the entire pore volume has production occurs. So these are some changes which are likely to occur between your P high and your PB. You know, your connate water expansion, that's the interstitial water, the water within the reservoir system, your SW, we expand as oil is produced. So as the oil is produced from the pores of the reservoir, um, the water expands, the water in the reservoir expands further. Based on the water compressibility. So although there is no water production, so you have to take note of that. But there is expansion of the connate water as well as produced. And there is also reduction in the entire pore volume as oil is produced, water expansion occurs, there's reduction in the pore volume. Okay, so this occurs between your P high and your PB. So I'm likely to find one or two more points added to this in order to understand the physics of your system between the P high initial reservoir pressure to the PB bubble point pressure. Okay, so let's go to the next example, quite an interesting one. The volumetric calculations of a well-developed gas cap drive. So this is a gas cap drive. We have treated the undersaturated, saturated reservoir, a reservoir in which there is no water influx. So here we are treating a well-developed gas cap drive reserve, and the result of the volumetric calculations shows the following. You have your N to be 763 SCB. In the previous examples, we estimated N. In this example, we've been given N, 736 times 10 to the power 6 SCB, okay, estimated at the surface. Your initial reservoir pressure to be given as this, your BG high, remember, given this, your G, this is the billion scuff of gas, 3,200 at the surface, your BO high, and your RSI. Beautiful. The production history in terms of parameter F and the PVD data are given. We should see it in just a moment. We are asked to estimate the gas oil volume ratio. That's the gas over oil volume. That's the gas cap size M. So your M, gas cap size, okay? So, and compare with the calculated value. Compare with the calculated value, okay? Okay, so we have the data given, the pressures 2803 up to 2798, quite pressures are quite close. And then you have your F underground withdrawal in barrel. You have this, okay, also quite close. You have your BT, two-phase formation volume factor. Remember why you have your BT, right? You have the reservoir is identified as a gas cap drive, okay? A gas cap drive reservoir. So you have your BT here, and then you have your BG. You have your BG. So for you to have your BG, meaning that you have reduction in RS, and then you have RP at the surface, but all that's not given in this equation. We are focused on estimating our the gas cap size. Okay, so you recollect from um, uh, videos 1 to 3, which we have earlier, your hem, gas cap volume and volume of oil in place. Okay, so you have the gas cap volume and then volume of oil in place, NBOI. So you have your GBGI, you're giving your G, you're giving your BGI, we're giving our N, and you're giving our BOI. Okay, so we have hem straight up 2.9, 2.9, and M straight up 2.9. That's the size of the gas cap. Okay, now let's make use of the production data. The production data. This is the volumetric data we're given. Let's look at what material balance says, the hem from the material balance. Okay, so for the gas cap drive, you remember this F, NEO plus MEG, your EO, NBT minus BTI, your EG, and then because your M is given, remember in this scenario, this case, when M is given, you have M equals F minus NEO over NEG, okay? Right, NEG, and then if you calculate your F, um, your F, your HEO, your EG, your HEO, your EG, you've been given your F, okay? You've been given your F. So all you need to estimate is your EO, which is N into BT minus BTI. N into BT minus BTI. Your EG is BTI into BG over BGI minus 1. Okay? So you've been given this. You have your BG. The first one is your BGI, and every other one is your BG. Okay, so it's quite easy to estimate this at the corresponding pressure. And then your HEO, your BT, N into BT minus BTI, quite simple. So you have your BT, that's your BT high here, 1.3904 for this guy here, and then the subsequent BTs. Okay, so it's quite easy to estimate. So you have your F given, your HEO, you estimate it, your EG, you estimate it, and quite easy. Yeah, there you go. Your M is F minus NEO. If you make your M the subject of formula and divided by NEG. So quite simple. Okay, quite simple. So you have the values of your hem. So at 2803, you have your hem to be 3.58. At 2802 pressure, PSI, you have your M to be 2.93. At 2801, you have your hem to be 2.48, 2.22, and then your M continuously decreased up to 1.73 or 2798 PSI, the last pressure given for the production profile. Okay. The estimated M is sensitive to the average reservoir pressure. Okay, it's sensitive to average reservoir pressure. From the volumetric data we're given, you have your hem to be 2.9, 2.9, and here you have your varying hems at varying pressures. So why do you think your M, especially between 2803 and 2800, 2802, why is it higher? Why do you think it's higher than the estimated hem? The estimated hem. Here, pressure is not involved. Pressure is not involved. Okay, insensitive. It's not sensitive to pressure. You only have the G, the BG high, your BO high, and your hem to estimate your hem. But here, you can understand that your hem reduces with pressure. As your pressure reduces, as production progresses, you have your gas cap equally reducing, the gas cap size reducing. So why do you have a reduction in the gas cap size as pressure reduces? Okay, so such a question could be asked I'm sure you have some answers to that. Under gas cap drive, go back to videos 1 to 3 and you understand what gas cap drive and its characteristics. Okay, so let's go quickly to the next example. We have here the production history and the PVT data of a gas cap drive. Also, a gas cap drive, here guy we have here, given below. So you have date, this is 5th of January, 1989, 1st of January, 1991, the 1st of January, 1992, 1st of January, 1993, okay? So this pressure was taken, and then the corresponding production data, you have the NP here, this possibly the initial reservoir pressure, there is no NP, there is no GP, okay? You probably have a two-phase, so because it's a gas cap drive, yeah, gas cap drive, so you have the oil phase and the gas cap phase, and then you have the BG, okay? And then subsequently you have this oil production from the gas, could be the condensate drops, okay? Because the gas cap drive have a whole volume of gas overlying oil, okay? Yeah. And then you have the gas produced, the BT, the BG, okay? So the initial gas solubility, RSI, is 975 scuff per STB. This is your RSI. Estimate the initial oil and gas in place. Estimate the initial oil and gas in place. So that's what we're going to be doing. The initial oil and the initial gas in place. Okay. Let's get right into it. So remember your gas cap drive reservoir, the Schilthius equation, which describes it. You have all this, you have here, okay? So in this case, M and N are both unknown. This is a case 3 treated under gas cap reservoir. So you may want to go back and understand what this case 3 is about. Under the case 3, you have this, and the plot of F over EO versus EG over EO gives this. You have your M, which is the slope divided by the intercept. The slope divided by the intercept. Okay. So remember to estimate your RP, because we're not given RP, right? So your RP, your GP over NP, okay, gas produced, well, oil produced. So you have 1525 scuff per STB. So you go ahead and calculate your RP at 3135 and 2845. Okay, you have the data. Okay, so you have your GP, and then over NP, GP over NP, you give you or your RP. So it's quite simple. Just divide this by this, and then you have your RP. Okay, you have your RP. Okay, so your F, NP plus RP minus RSI BG. Okay, so at 3875 PSI, you have this. You have this slot in the values, the corresponding values to the pressure. You have this. Okay, so calculate for 3315 and 2845. Okay, let me go back. Okay, again, because you do not have NP here, you don't have BG, you wouldn't have RP. Okay, so it was calculated for 3875, 3315, and 2845. Okay, so you go ahead and calculate your F, for at 3315 and 2845. Do the calculations. Okay, so and likewise your HEHO at 3875. Your EO is BT minus BT high, which you have 0.054. So you calculate your EO at 3315 and 2845 PSI. So if you key in the values in the production data you're given, just key it into your Excel, or you do it by manual calculations, punch your calculators. Okay, you have these values. And then your EG is BTI, BG over BGI minus 1. So at 3875, you have 0.0423. So you calculate your EG at 3315 and 2845 PSI. Okay, so you get all that. So you have your EO, you have your EG, you have your F, EOF, your EO and EG. Don't forget, you have your RP, GP over NP, which was the first calculations we did. Okay, so quite simple. Just for you to know the Havlena and Odeh for gas cap reservoir, and then you apply it to your pressure, your production profile data. Okay, so if you plot your FEO, that's what we are plotting here. If you plot it by EG over EO, okay, some of these data values here are not quite correct. So try to do your own calculations and then plot. You have a plot similar to this, okay? It goes right here. Note that the plot does not go through the origin, okay? Like in other cases for gas cap reservoir, when you are estimating your M and your N, when your M and your N is not given, your plot goes through you have an intercept on your y-axis, okay? So the intercept here is your N, so you estimate your N, do the calculations and estimate your N, do your plotting, do your manual plotting, estimate your N, and then which is your slope, which is your intercept here, and then estimate your slope, your slope. Your slope is your MN, okay? I believe you understand that. Let me go back, show you here. From here, you are plotting, you have F over EO, you are plotting it against EG over EO. Your slope is your MX, okay? Y equals MX plus C. This is your C. Your N, that is the intercept. Then your MX, X is your EG over EO, which was plotted on your x-axis. And then your M, which is your slope, equals MN. Don't forget your N is the initial oil in place, and your M is the gas cap size. All right. Okay, so let's go back. Okay, so that's what you have here. Your slope, which you estimated here, is your NM. You have your N already here from the intercept. Okay, so then you estimate your M. Fantastic. So you're able to estimate your N and estimate your M. All right, so lay your hands on the calculations. Try out at each pressure. Okay, so let's go to the next example. You have here another interesting question that says the calculation of recovery factor for an undersaturated reservoir was done with no water production, as WP is equals 0, and negligible water influx. You're familiar with this now, WE equals 0. The calculation was performed with and without including the effect of compressibility. So this is quite interesting. We want to see the effect of compressibility on our reservoir drive, okay? Assuming that the critical gas saturation is not reached until after the reservoir pressure drops below 2200. You understand what this means now? Okay, so once the critical gas saturation is reached below the bubble point pressure, gas flows to the surface. But this wouldn't happen. I mean, gas wouldn't flow to the surface until your critical gas saturation is exceeded. Okay, so this interesting question we have, it's an undersaturated reservoir. There is no WP, there is no WE, they are both 0. And then you have the effects of compressibilities and to be examined, okay? So you have the data given, your initial reservoir pressure 4,000 psi, your ball point pressure 2,500, you have your SW 0.3, you have your CW, you have your porosity 10%, your CF also in the same order with your CW. Okay, so let's go. So it's an undersaturated reservoir. So we have all this. Okay, I'm sure you're familiar with this now. You're familiar with all this. all these equations. By now, you're familiar. Okay. Um, so here, it's in two phase. You have gas and the oil phase existing. Okay. So you have your HEO BT minus BTI, your EFW examined as BTI, as this. Okay. And then your MP over N, your MP over N gives you this. So if you make N the subject of the formula, okay, so substituting, okay, equating NPBT to your N, this is your F NPBT, and you have this NEO plus EFW. So if you equate this and this is your left hand side, this is your right hand side. Okay, again, you may not fully understand this if you are just watching this video. Go back to the channel, and there are videos on material balance equation, part 1, part 2, part 3. All these equations have been fully explained in the videos, so you will understand all this if you go back and watch the videos. All right, thank you. So you have the HEO, and then you have the EFW. Then if you make MP over N the subject of formula, you have this. So without, this is with compressibility, effect of compressibility is above PB, above PB, okay? So you have MP over N to be this, okay? Uh, so let's go. So assuming the effect of compressibility is not negligible, the effect of compressibility is not negligible, meaning that we added the effect of our compressibility to the estimation of our recovery factor. Okay, so you have this equation. You slot in at 2,500 psi at bubble point. You have all the corresponding values. Again, let me go back so that you can fully understand it. This is the equation. Okay, equation. So above the bubble point pressure, okay, you have your MP over N. The MP over N is the equation here. Okay. So you slot in your BT, your BTI, CW, SWI, CF. Okay, you slot in all the equations, and then you have this. With effect of compressibilities below PB. Okay, below PB. Now, the effect of compressibility, the effect of compressibility at bubble point, the pressures that were given, you have 4,000, and then you have 2,500 psi. Okay, we are asked to calculate the recovery factors under the two conditions at the undersaturated state, okay, and then below the bubble point pressure, okay, below the bubble point pressure. So that's what we are trying to do right now. Okay, so for the undersaturated state, the effect of compressibility was added for the undersaturated state. So you have this estimated recovery factor at bubble point pressure 2,500 psi. Okay, with effect of compressibilities below PB, at below PB, your RP is not equal to RSI, is not equal to RS. So you have your MP over N, okay, effect of compressibility, and then below PB you have this, okay. So you have this. Then RP is the total net gas produced up to any period divided by the total oil produced. So you have, because you have RP here, and we do not have RP, you can see there's no RP in the table pressure profile we're given. So we have to estimate our RP. And RP is the summation of the NP multiplied by R divided by NP. Okay, so because we are trying to um, solve for NP over N, so we divide both sides by N, we divide by N. So you have NP over N, summation NP over N, NP over N. Okay, we have this. Then we go ahead to substitute this into this equation, okay, in order to estimate the NP over N. We substituted this RP in here to estimate NP over N. Okay, so that is what was done here. All the equations here were the values were slotted into this equation. Okay, and then you have your RP here. You have your RP, and then the NP over N comes in. So you have a bit of rearrangement, okay? And then you have the average R, which is 1000 plus 920 divided by 2, that's 960. And then that comes from your average R. Okay, if it is between 4000 and 2500, like you have here, it will be 1000 plus 1000 divided by 2. Between 2500 and 2300, you will have 1000 plus 920 divided by 2. Between 2300 and 2250, you have 920 plus 900 divided by 2. While between 2250 and 2200, you have 900 plus 880 divided by 2. So depending on the pressures that you are considering, okay, the drop from 4000 to 25, the drop from 25 to 2300, the drop from 2300 to 2250 psi, and the last pressure drop from 2250 to 2200 psi. Okay, so here is between 2500 and 2300. So we have our average, which is 1000 plus 920 divided by 2, that's 960. So you slot it in here, you slot this here, and then you slot the whole of this into this equation 1. I hope you understand that. Okay, this is the R average that was calculated. I went back a slide. This is the R average that was calculated. Is actually the R average. So after calculating the R average, you slot in here, and then this summation NP divided by N multiplied by the R average, you slot it in here because the whole of this is your RP. So you bring your RP into this equation. Okay, so you have this. So substitute R average into your equation 2, and then solving equation 1 and 2. So I want you to try to solve this equation. This substitute into here, and then solve. Okay, you have this as 960 already. So you have NP over N only left in this equation 1. You have NP over N here, and then you have NP over N here. So if you rearrange, and then solve for your for the equation, you will have your NP over N between 2500 to 2300. You will have 0.08391. At 2300 to 2250, you will have 0.11754. Okay, so you try out at 2250 and 2200. You try it out. Okay, so the first part we did assume that the effect of compressibility is not negligible. So effect of compressibility was added. Now, let's assume the effect of compressibility is negligible. Okay, again, let me go back to the question so that you understand that you're on track. You're on track. It says calculate the recovery factor for an undersaturated reservoir. Okay, it has no water production, it has negligible water influx, and the calculation uh, was done both with and without effect of compressibility. Okay, then assume the critical gas saturation is not reached until after the reservoir pressure drops below 2,200 psi. Okay, so we are asked to calculate the recovery factors under the two conditions. Under the two conditions, when uh, the compressibility was negligible and when compressibility was not negligible. Okay, so let's go back to the second part that says, assuming the effect of compressibility is negligible. So the effect of compressibility is negligible. You have a recovery factor at bubble point pressure, 2,500 psi. What do you have? Because the effect of compressibility is negligible, so your MP over N is BT minus BTI over BT. Okay? So you have your MP over N to be this. Okay? And here is just BT because RP equals RSI at the bubble point pressure. You remember? Below the bubble point pressure, that is every other pressure below bubble point pressure. Okay? RP is not equal to RSI. And that is why you have this. And remember, uh, your RP, you have to estimate it. Your R average, remember? So you slot in this, okay, into your RP, and then you estimate your MP over N, okay, below the bubble point pressure. Okay, so between 2,500 and 2,300 psi, this is the pressure below the bubble point pressure now. You have this, your MP over N to be this, okay? You must have calculated your R average. Your R average, remember, you must have calculated the R average. You slot it into here, and you slot this, into RP, your RP, okay? So you have this, slotting in your RP, you have this, okay? Your, okay, this is your RP, is your RP. Your R average is 960 because it's between 2,500 and 2,300 psi. So your R average is 960. You bring your 960 here, okay? And then taking this whole equation and slotting it into here, you will get your NP over N to be 0.07051. If you try at 2,300 as it drops to 2,050 psi, your NP over N estimate to be 0.08707, okay? At 2250 to 2200 psi, you have your MP over N to be 0.10377. So I want you to lay your hands on the calculations, and then if you have a plot, the pressure versus fractional recovery, the pressure versus fractional recovery plots. So this is the pressure you have between 2,000 to somewhere around here, 4,000. You have the fractional recovery obtained with compressibility. That was plotted here. That's somewhere around there, 0.2322, somewhere around here. This is plotted against pressure, okay, about 2.5, okay, and this is plotted 0.088485 plotted here. 0.10, 0.12. Okay, so this is with compressibility terms. And here you have without compressibility terms. So what is the difference between the two? Both of them are sensitive to pressures. Okay, both of them are sensitive to pressures. And here with compressibility terms, you have higher recoveries, higher fractional recoveries than without compressibility. Without compressibility. So you may want to ask yourself, should compressibility terms be added to our calculations? Okay, below the bubble point pressure, above the bubble point pressure, at the bubble point pressure. Okay, what's the bubble point pressure? The bubble point pressure, can you check that again? Let's go back so that we remind ourselves effectively. Okay. Bubble point pressure is 2,500 psi. The phi is 4,000. Okay. Bubble point pressure is 2,500 psi. Okay, so you see here 2,000. Let's go 2,200. So somewhere around here, let me move this up. This is about 2,500, 2,200. Should be somewhere around here. Okay. So we see the effect at somewhere around here. So should effect of CG, compressibility times, that's CO, CW, below the bubble point pressure, should it be added to the drives while estimating our recovery factor? Okay, just a bit higher here. The one with compressibility terms, the recovery factor a bit higher. So it's sensitive to pressure. It's sensitive to pressure. So below bubble point pressure, especially when you have uh, gas reservoir, gas cap drive reservoirs, solution gas drive reservoirs, you have your CG to be far, far, far higher. Remember, we discussed it in the class where your CG is far, far, far higher. Okay, but it's still worth it to add the CW and the CF like we did. Let me go back a bit again so that you can see. Just a minute. Okay, so the effect of compressibility here was not negligible. We added it here, and that's where we have that plot, or the NP over N that we got. Here was not, this is at the bubble point pressure. So at the bubble point pressure, remember your RP also equals RS cos RSI. That's why we have just this as the denominator. And below PB, you have this, and then you estimated your RP. So here it is not negligible. Okay, your CW, your CF, raw compressibility, and water compressibility below the bubble point pressure. Okay, at bubble point pressure of 2,500. 2,500. But it was stated in the question. It was stated in the question that the gas did not actually begin to flow up until the pressure dropped below 2,200. That was when you have gas production to the surface. So that means you've been having expansion of gas within the oil system, driving the uh, production of oil. Okay, despite that, the PB was 2,500 psi. Yeah. So if you have added effects of compressibility, your rock and the water compressibility between 2,500 and a little bit higher than 2,200, because you don't want to get to the point, you want to account for that effect of your water raw compressibility, just below the critical gas saturation pressure. Okay, so you will understand if it actually have an effect on that flow of the reservoir. Okay, so here, coming back here, if we look at 2500 psi, which is the PB given, 2500 psi, here you have your MP over N without compressibility term to be somewhere here at 2500. Okay, you have here uh, around 0.118 thereabout. And then with compressibility, see, it's far higher. With compressibility, it's higher. Yeah, it's higher. So you want it to add the effect of compressibility to your drive while estimating your recovery factor. So if you neglect it, you may be underestimating your recovery, your N, especially your initial oil in place, and how much of that N that can be produced, over time, the life of your reservoir. Okay, so I'm sure you've learned a lot with these examples treated. Um, Here says plot the pressure versus fractional recovery profile, okay, which was plotted. Explain the significance of compressibility factors on recovery, which we are trying to discuss the effect on when you have between your bubble point pressure and critical gas saturation pressure, and between the critical gas saturation pressure downwards. Okay, so what happens? Does it have effect? Is it significant? Is it effective? Can we underestimate the value of our recovery, fractional recovery, while neglecting compressibility factor? Okay. Then number 4 says briefly discuss the two fundamental production mechanisms in undersaturated reservoirs. Okay. So I'm sure you can give the questions a short. These are things we have discussed before now in our previous videos. Okay, so you have lastly an exercise here. So I want you to lay your hands on this exercise. It says the following data are taken from an oil field that had no original gas cap and no water drive. And you are given this, the oil pore volume to be this, your bottom hole pressure 140°F, the compressibility factor of the gas to be 0.95, that's your CG, and then your net cumulative GOR, that's your 2000 at 2000 scoff per STB. So you're asked to calculate the following from 1 to 11. I'm sure you can likewise give it a shot. The initial STB of oil in the reservoir, initial SCF of gas in the reservoir, your reservoir volume of free gas at 1500 psi, your dissolved GOR. Okay, so you have to calculate all this. I think I actually kickstarted it for you. It's an undersaturated reservoir. We were told there is no water drive and no gas cap. Okay, I believe you can remember that. Okay, it says no original gas cap and no water drive. Okay, so you have this, you have all this. But for you to calculate the initial STB of oil in the reservoir, you have to calculate the initial STB of oil in the reservoir. The first question. The volumetrics, you have your oil pore. You were given the oil pore volume, which is AH5 1 minus SW occupied by the oil. Okay, oil pore volume. You have this. Oil pore volume was given as 75 reservoir barrel. Okay, so from your estimation of your N, okay, 7758 AHY 1 minus SW divided by your BOI, you have 775.606 times 10 to the power 9 STB. Okay, so I want you to give the many questions a shot. Try to make use of your volumetrics. Try to see if you can make use of your MBA as well, and give the questions a shot. Um, yeah, thank you very much. So as we did a recap of volume 1 to 3, we treated examples, and likewise, I gave you an exercise. All right, so I'll see you in the next video. Thank you very much for listening.